everyone. My name is Amitai Uzrad. I am a PhD student under the supervision of Dr. Shay at Tel Aviv University in the Faculty of Electrical Engineering. And I will be discussing our paper, Dynamic 1+epsilon LAN and Approximation algorithms for minimum set cover and dominating set. These two problems are very similar. They also have their differences, but I will be only focusing on minimum set cover due to time constraints now. So I'll just give a bit of an introduction for static set cover. So we have n elements and m sets, and each set contains a subset of the elements, and it has a cost or a weight associated to it. And our goal is to find the the least costly collection of sets that cover together all elements. We have the frequency f, which is an upper bound to the number of sets that can contain any element. And we have the aspect ratio C, which is the ratio between the most expensive set and the cheapest set. We normalize the weight such that the most expensive set has weight 1 and the cheapest one has weight 1 over C. So there are two algorithms for obtaining an approximate solution in the static case. There's an F approximation, which is primal dual, which we won't discuss at all. And there's a LAN-N, which is a greedy algorithm. It works in iterations. In short, in each iteration, we choose a set that maximizes the ratio of the number of still uncovered elements over the cost of that set that we are considering. We want to maximize this, and then in each iteration, we remove the newly covered elements from the set of uncovered elements, and we continue until all elements are covered. In the dynamic setting, we have elements that are inserted and deleted each update step. The sets are static, the sets and their cost. Throughout the update sequence, the maximum number of elements is n, and the maximum frequency is f. Some previous results. So the first 5 results here, you can see they rely on the primal dual methods. You can see from the approximation ratio that they are dependent on f. They use primal dual methods. And the last one is the state of the art that relies on greedy. It gives an O log n approximation. The constant inside this order of log n is relatively high. And their update time, amortized deterministic, is order of f times log n. So the constant here is over 1,000. This is by Gupta et al., published in STOC about 6 years ago. So all the coefficient, it can be improved. In their paper too, they didn't try to even optimize it, but they use a local algorithm which has its constraints, which we will discuss also here, and it can't be improved beyond 81 or 27 if we allow polylog update time, f times polylog. So it can be improved to some extent, but it's still far from 1. Now 1 is what we aim for, 1 times LAN-N approximation factor, because that way we coincide with the static, and that's the best we can hope for, because we can't hope to do better than static. So our result is the 1+epsilon LAN-N approximation, very close to what we such as the holy grail, let's call it. And the update time, the amortized update time, that's a deterministic algorithm as well, is order of with a small epsilon there of f times log n. So that means the same update time if we neglect epsilon dependencies. Our epsilon dependencies are polynomial in 1 over epsilon, epsilon to the power of -5. So if we neglect that, epsilon we consider it as a small but constant. So so if we disregard that, we have the same update time, and we improve the approximation factor drastically. Okay, so some preliminaries. So U is a dynamic collection of elements, and F is the static collection of sets. Their weights are static too. Now, what we maintain is not a collection of the sets that are in the set cover. We maintain an extended solution. And what that means is that for each element, we have a specific set that is responsible for that element, that is responsible to cover that element. That each element has a set that covers it, and it has only one set. So each element is we can think of it as assigned to a specific set. only one set, and each element has to be assigned to a set. So these are called cov sets. So they are subsets of the set. So you can see here that cov S1 is a subset of S1, and it contains all the elements in S1 that are assigned specifically to S1. That S1 is responsible to cover them. And our solution, the set cover, is all sets such that their cov set is not empty. So therefore we get a valid solution. So in this case here, we can see that there are elements in S4, the yellow-orange set, but they are all in cov S3, meaning S3 is responsible for covering them. Thus, the cov set of S4 is empty, and S4 is not in our set cover. So in this specific snapshot, our set cover will be S1, S2, and S3. Like I said, the set cover is the union of all sets that their cov set is not empty. Okay, so each pair will be placed at a level according to the ratio of the size of cov S over CS. Now, notice that this ratio is exactly what we want to maximize when in each iteration of the greedy algorithm, in the static case, right? We want to choose a set S such that cov S, we can think of it as the uncovered elements, right? Because cov S is exactly each element is in one cov set, so these are the same, these are completely analogous, and but we want to place at a level according to the size of cov S over CS, and each level j is defined by the range beta to the power j to beta to the j plus 1 for some beta larger than 1, and if a pair is at level j, then all of the elements in cov S, if S is at level j, then all the elements in cov S are all covered at the same level, and we say that they are covered at level j, and we say that S is covering at level j. And a pair is clean if the ratio is in the range, meaning if it's where it's supposed to be, it's an appropriate level. And if all pairs are clean and all elements are at the highest possible level, then we coincide in a sense with the static to yield a good approximation factor. We only coincide with quotations because we kind of quantized our levels. We have a kind of discrete system here. So there's still this beta factor that if we think of it as buckets or something like that, then it still adds some kind of factor. But if all pairs are clean and all elements are at the highest possible level, then up to that beta factor, or beta to the power of 3 or 4, we'll see, it's the same as the static algorithm. Because if we want an element to be as high as possible, this in the static case means that we want an element to be chosen earlier, the earliest as possible. And that's it. Okay, so the algorithm, we have insertion. So once E is inserted, all we do is just add it to the cov set of the set that contains it in the highest level. So we want elements to be at the highest level always, right? And if E is deleted, we just leaves the cov set it is in. Now, we can't guarantee that all pairs will be clean. All of the sets will be clean at all times, right? Because if we have a set that is clean, and now we have deletions, the adversary deletes elements from a certain cov set, at some point, it'll leave its clean range, right? Because cov S will be smaller and smaller. And then we can offer ideal guarantee that is again, that sets are clean and the elements are at the highest possible level. So if the set gets dirty, we fix it as follows. We define two invariants, positive dirty and negative dirty. So S will be called positive dirty if it can move higher and take to cov S elements covered low. This is just the exact definition. I'll just continue from here. So cov S, let's look at a set S. It has, let's say cov S1 and cov S2 are at a lower level. And so these are low-level elements. All the elements in cov S are the same level. All the elements in cov S2 are the same level. And so if S can take all of these elements to a higher level and we create cov S at a higher level such that it is clean, meaning that the size of cov S over the cost of S is in a clean range, is between beta to j to beta j plus 1, and this j is higher than all the levels that they were in, then we call this a local rise. And if that's the case, then S is called PD, positive dirty, and we just do a local rise, so it's not dirty anymore. In other words, what S did here is that it took a bunch of elements that were at a low level, it raised their level, which is more ideal. And by doing such, it's still a clean set. It's a clean call set. So by doing that, we are in our ideal guarantee that the sets are clean and that every element is at the highest possible level that it can be. So as long if a set exists if a set can raise a bunch of elements that are at a low level to a higher level, and then that newly created conv set will be clean. If it can do that, then it is called positive dirty, and our invariant is that there are no positive dirty sets, because once such a set exists, we do a local rise, meaning we create that set at a higher level. Negative dirt is a bit more simple. So the range for a level j is between, we want the size of Covas over CS to be between beta to beta j plus 1. If it deviates to the negative side by a factor of more than beta, meaning this ratio is less than beta to j minus 1, then it's called the negative dirty. This could happen if many elements leave the Cov set, either because of a local rise or because of a deletion. And in this case, what we do is we simply drop of S to a suitable level such that it would be clean. And this way, so that's our invariant, that there are no ND sets, because once the set is ND, we drop it to a level such that it is clean. With these two invariants, you can see that we maintain the fact that all sets will be clean, or they won't be too dirty by a factor of more than beta. And also all elements will be at the highest level that they can be. Okay, so these two invariants take care of those, which helps us coincide up to a factor of beta and a bit with the static case. Okay, so like we said, we went over the insertions and deletions, and once there's a local rise, so Covet will rise, and falls, we also discussed this. Okay, so now when we want to analyze the update time here, our first and main step is to analyze the amortized number of element level changes. Because after each element level change, we want the element to update the set that contain this element, that it changed its level so that it could know if it needs to do a rise or a fall. So it needs to update the relevant data structures, but the main challenge here is to analyze the number of element level changes. After that, it's a bit more technical, dealing with relevant data structures, etc. So when do elements level changes? When do elements change levels in insertions, deletions, rises, and falls? So the problem is that a local rise can trigger a fall, which can trigger a rise, and so on. We'll see an example here, and all within a single update step. So it's not clear that this cascade of falls and rises terminates, let alone yielding a decent update time. Even though we're aiming for amortize, it's still not clear. So let's see how this can happen. So let's say we have Covis 1, and all these elements in Covis 1 on the right, they belong to some S set S2. Let's say that they're at a relatively low level. So Covis 2, S2 wants to do a local rise, causing ND to be, causing Covis 1 to be ND, which does a fall. And now due to this fall, S3 now, let's say all these elements are in S3. S3 is now PD because it gained now new low level elements, the ones that were in Covis 1. So now S3 is PD, does the rise, and this can continue on and on. So we'll use a token scheme. Each insertion, each element that is inserted will receive x plus 1 times log in the base of beta n tokens. X plus 1 token, and this is because each element, we won't go into the details here for due to time constraints, but each element can only be covered at log beta n levels. Those are each element has those levels that it can be covered at. It can't be covered at more levels. So we will give for each level that it can be covered at, x plus 1 tokens labeled for each level. So let's say those levels are 0 to log beta n. It has log beta n plus 1 levels that it can be covered at. And so we give it x plus 1 tokens labeled 0, x plus 1 labeled 1, and so on. Each insertion. And once an element changes its level, we want for it to pay 1 token. So if we prove that our token scheme doesn't run out of tokens, then the amortized number of element level changes is upper bounded by x plus 1 times log and base of beta n. And x is just is going to be some constant. So we can show that it's the number of element level changes is order of log in the base of beta n. Okay, so how we do this is that if E is in a local rise from J1 to J2, J2 from level J1 to level J2, so it pays one token for the level change. That's what it needs to do for the token scheme, but it also leaves behind X tokens labeled J1 to its previous covering set F. The main issue is that E can be covered at a level multiple times, okay, because of faults. If it only had rises, let's say there's an element E that only rises from level 2 to 4 to 7 to 11, and so on, then that's okay, right? Because once it's inserted, it gets all of these tokens labeled, all of the levels that it can climb. So for each level it goes, it has the token labeled, the tokens that it needs. But the problem is that once it gets to 11, it can fall back to 2 due to a local fall, and then it needs to again climb to 4 to 7 and back to 11. But it already spent those tokens labeled 4 and 7 and so on the first time it rose, and now due to the fall, it won't have again. But what we will claim is that if a set falls, then that is because many elements left it. And if those elements left it, they each left X tokens behind for the set. And these X tokens that are left behind from each element, they can be redistributed to the elements in Coves that do the fall, such that they can have enough tokens to climb back to where they were before the fall. So let's see what I mean exactly by that. So let's see all these elements lead to a local rise. Each leaves X tokens. We have a huge pot of tokens now for Cov S. And then a Cov S is ND because many left. It drops the Y level. But I have enough tokens. What I want to do is I want to have enough tokens, meaning Cov S obtains enough tokens from the leaving elements, such that it can redistribute Y times X plus 1 tokens for each element. That way, each element can climb back up to the level that it was before the fall. In other words, our invariant is that for any J, any level J, every element at level J has X plus 1 tokens labeled J, X plus 1 tokens labeled J plus 1, and so on until the highest level that it can be in. And that's it. Okay, so to maintain, we have some kind of recharging scheme here. We need beta to be, we'll show why it needs to be at least larger than 2. So let's say if beta is small, that means that it's enough that just a few elements leave, and that this causes the set to be ND, right? This is a Cobb set, the oval here. So it causes the set to be ND, so it does a local fall. But each of these 3 elements only left X tokens behind. So we can't hope to redistribute for each remaining element X tokens for each level, right? We need that the majority will leave, as we can see in a large beta. Only when a majority leave in a large beta, then it's considered ND, and then we have enough tokens for the remaining in the COP set to do the to have enough tokens to climb back up to the level that they came from. And beta, so this means we have to take a large beta, and beta to the power of 4 will be the coefficient of Lannan in the approximation factor. So we get more than 81 because beta will be larger than 3. So to do better, what we must do is, or what we do is we change the algorithm to be more global. And what do we mean by that? We won't allow local falls, right? Because we saw that this kind of, this makes life harder for us. So what we do, we will relax our ND invariant in a global manner, saying that on average, the sets together are not ND. So if some are ND, but the minority, but the rest are not ND and they're very clean, then that's okay with us. And that's just what we do. And we fix beta to be 1 plus epsilon. So now ND means that about an epsilon fraction of elements left. So here we have an example. This is a very loose definition that what I'm saying that we relaxed it so that on average they're not ND. Obviously, there's many more details here. This just to give a kind of a hand wavy idea. So here on average, it is ND because there are 2 that are ND and 1 that is not. So we consider the system to be ND. So once the system is ND, what we do is we perform a reset up to a critical level. We still do local rises, but this is just how we take care of falls. So what do I mean by a reset and what do I mean by a critical level? A critical level is just a level. We won't also get into details of that, but what let's just say that once the system is empty, there exists a critical level that I can do a reset up to. And what is a reset? A reset is just the greedy algorithm on a sub-universe of elements and on a sub-family of sets. And it cleans up all the clove sets up to that critical level. So let's see exactly what I mean. The y-axis here is the level axis. And let's say that the system is dirty, the system is empty. And so we have a critical level, which is the red dotted line. So all the elements beneath the critical level here, we take them out of their clove sets. And we take also all the sets that we're covering at a level up to the critical level or not covering at all. And we just run the static greedy algorithm on this sub-universe and sub-family of sets. That's all we do. And then each set which is covering as a result of this static algorithm procedure, we place it at an appropriate level such that it is clean. So the observation, first key observation is that following a reset where S participates in meaning it was in the subfamily that we consider, it is clean. That's by just definition of the by the description of the algorithm. What we do, we place it at a level such that it is clean. Okay, this is the definition, the exact definition of PD that I had on before. So S is PD if exists a level J, which is larger than the level that S is covering at, such that the number of elements at level less than J in S is at least CS times beta J plus 1. Now, another observation is that following is that if S participates in a reset, it was in the subfamily of in the greedy algorithm, then for any J up to the critical level, the number of elements at level less than J in S is less than CS times beta J. That means that S needs to acquire a beta factor more new low-level elements to be PD since the last time it did a reset. So once we have a local rise of S to level J plus 1, we look at the last time that S did participated in a reset up to that level at least. And at that point, the number of elements of low-level elements that it had was less than CS times beta J. And by the time it was PD, it had more than CS times at least, CS times beta J plus 1. That means it obtained CS times beta J plus 1 minus CS times beta to the power of J. It obtained this amount of new low-level elements. Now, how can a set obtain new low-level elements? Either by insertion, right? If an element is inserted and it chooses the highest clove set, the highest level clove set that contains it. If this is less than J, then that's a new low-level element less than J. And another option, since we don't have false, is by reset, right? Reset is the only way that an element can drop its level, right? From rises, they only rise. From deletions, they just exit. From insertions, we went through that, and reset is the only other thing, okay? So let's look at this reset. So let's say that we have S, a set, and we have an element that was at a level higher than J, and now is at a level lower than J. It dropped due to a reset. For this to happen, though, S would have to participate in this reset. Because had S not participated in this reset, meaning S would have been higher than the critical level over here, then we won't be able to have, then that means that J was also higher than L cov S, because that's by the definition of PD, J needs to be higher. That means that an element higher than S would have to fall, but an element higher than the critical level cannot fall because it doesn't even participate in the reset, right? So for this to occur, S would have to participate in the reset to obtain a new low-level element. But if S participates in a reset, then by the previous observation, it's still beta far from being PD. It's still the number of low-level elements it has is less than CS times beta to the power of J. So in a sense, we're still back to square A, and we still need to obtain a beta factor more low-level elements. So resets can't happen. We can't have new low-level elements. So each new low-level element comes from insertion. And this is good for us because insertion is the adversary, and that means that there are more update steps, and we can charge the local rise from these insertions. So we can afford all local rises if insertion gives 1/epsilon tokens per level. Okay. Why? Let's just see. Go back here because I had CS. Let's say I had up to CS times beta j and low-level elements, and now I have CS times beta j plus 1. If I do the difference between these, that means a beta factor. A beta factor more means that an epsilon fraction of them are new. So if an epsilon fraction of these elements are new and they came from insertions, if each one pays 1/epsilon, then I can charge the rest. Okay, last problem is so we can pay for PD sets as we just showed. Can we pay for elements changing levels in a reset? So we can. This is not too complicated too, but if each leaving element leaves behind 1/epsilon tokens the previous covering set, then we can pay. Why? Because ND, the way we define now ND, is we said that, and instead is ND, we said that before, if an epsilon fraction of the elements left it. So if an epsilon fraction of an element left the cov set, and each one leaves behind 1/epsilon tokens, then we can redistribute, this set can redistribute 1 token per remaining element, so that it will have a token for the level change. Okay? So in total, we have 1/epsilon squared tokens per level per insertion. Okay, now let's see this in a bit of visually. Hopefully this can maybe clear some stuff up too. So let's look at a graph that represents the level that F covers at as a function of the time. So we have rises throughout, and we have these falls that are from reset. And let's consider a specific point here at time where S rises to level j plus 1. It rises to level j plus 1 because it was PD. It was JPD, and it had more than CS times beta j plus 1 low-level elements at level lower than j, covered at level lower than j. Now what we do is we can, like we said, we look at the last time that S went through a reset up to at least that level. So there could be other maybe resets here, but they were not higher than this blue dotted line. So we look at the last time that it had a reset that was higher. And at that point, after that reset, we, from our previous observation, we know that that the number of low-level elements is less than CS times beta to the j. So we know that in this interval between this time over here and this time, we have gained epsilon times CS times beta to the j new low-level elements. Now, these low-level elements, we can, since they are an epsilon fraction of the elements that are rising. Therefore, if each one gives, as we said, 1/epsilon token, then we can redistribute for the whole rise. So the conclusion is that we have a 1+epsilon line in approximation, right? Because we had the beta to the power of 4. Beta was 1/epsilon. We can scale down epsilon. And our amortized update time is order of epsilon, f times log n. Like we said, we only considered here the level changes, which is just O epsilon log n. But the F comes from the fact that we need to update relevant data structures, notify for each element all the sets that contains it, which is up to F. We won't get into that details. But a main open problem is to remove this log n dependency and just stay with O epsilon of F, either by a randomizer deterministic algorithm. And that's it. Thank you very much for your time.